We welcome Maciek Wielgus from the Instituto de Astrofísica de Andalucía in Granada. So Maciek will talk about accretion beyond the black hole paradigm, like within the shadow. There will be time for questions at the end as usual, but feel free to ask also during the talk. And you have the floor. Thank you very much for being here.
I heard a lot about your group and your excellent results. I hope the talk will not be too simple for you. I will try to do some, I think, maybe basic stuff to talk about and just engage, let's say. Right. This is what ChatGPT thinks the alternatives to black holes could look like. I think this is wonderful. I don't know what this is. Looks interesting. Okay, so first I will start with an advertisement. The new part of this talk, other than just kind of talking about things that many people know, is on archive 2 days ago. So we've been working with Saura, who was also visiting here a while ago. He's a PhD student at the Max Planck Institute of Radio Astronomy in Bonn. And after like 2 years of a lot of work, intensive work, we finally completed a paper. The fun part of this paper is that we see a horizonless object that can actually accrete. Like the matter can fall into this compact object. It's not expanded in outflows. It's not accumulated in the system. And I will argue that this is an important feature if such an object is supposed to act as a black hole mimicry. And you may disagree with me, and then we'll have a nice discussion. Okay, so the part about overview and things that like everybody here knows, but I still think it's nice to talk about it. So be upset if I'm gonna say will be too simple for you. Let's try to reduce the story how that happened. Today we live in the world in which scientists operate under sort of what we would call a black hole paradigm. We know that there are very compact objects in a center of galaxies, from energetic considerations. We assume that they are black holes. And why do we do that? I will discuss that. So we turn back to 1910s, the formulation of general relativity, and the solution that followed pretty much immediately after the formulation of the field equations, the Schwarzschild solution that we all cherish and know for a static, spherically symmetric black hole, a vacuum solution to the Einstein field equations. And there are two features in this solution that are, let's say, weird. Event horizon was particularly weird when it was formulated. Einstein and others thought that it implies like a serious singularity at the event horizon. Only some years later, we learned that it's a coordinate singularity, so we stopped worrying about it. But all the paradoxes related to things happening in one frame and things never happening in the other frame are disturbing. So conceptually, there is. And singularity is a different problem. The central singularity, it is actually not a coordinate singularity, it's a curvature singularity. It really implies that the... I can't hear the talk. Well, that's okay.
We were, yeah, it was just...
Wait, but they said they can.
They can.
Okay, perfect. Okay, so this really is something that implies limitations of the theory, of course. Treatment of the singularity, which is beyond the manifold, the boundary condition feature, is something that the general relativity cannot do and doesn't pretend to be able to do. So there is this disturbing thing. I said that horizons are at least formally okay, meaning that we can do math and we can calculate how things behave interacting with the event horizon. The math is fine. There's nothing exploding, division by zero. So this is fine. However, we do know since 1970s that there is indeed a problem with horizons related to the information paradox. So horizon is okay, but if black holes evaporate, the information will disappear. And not in the way as we sort of sometimes colloquially think about it. You have a book full of information, you throw it into a bonfire. Did you lose the information? Well, like yes, for practical reasons, no, for fundamental reasons. The information is not vanished from the universe. It's different with evaporating black holes. The information is actually disappearing in the most fundamental sense. It is a problem. So horizons do give us not only conceptual problem, like does a person ever fall through the event horizon if the distant observer doesn't see that happening? It actually gives us more serious physical problems. It's just to argue, be the devil's advocate, that black holes have many problems. It's not that this is such a solution that don't produce any complications. Now, of course, as you know, when the black holes, when the Schwarzschild solution was introduced, Einstein wasn't enthusiastic about existence of black holes, the physical realization. So Einstein's argument was mostly that, well, it might be, it is the solution to the field equations, but perhaps, or most likely, there is no path coming from a regular initial state going to these pathological solutions. So that was proven to be wrong by Oppenheimer-Schneider, who showed that the most simple context of a collapsing material, a ball of dust, collapsing gravitationally forms a Schwarzschild black hole. So there is perfectly reasonable initial solution that don't involve any pathologies, ending up with a Schwarzschild black hole. So Einstein was proven wrong here. And then we had theories of Penrose, who found that I wrote horizons because this is like a popular part of the talk, trapped surfaces, fine. There is this implication that formation of trapped surfaces will result in singularity. There are many variants of the Penrose theory under different detailed assumptions. This is the work for which Penrose got the Nobel Prize in 2020. Penrose speculated that, well, perhaps this handling the implication could work also in the other direction. Maybe it's not just horizons that would imply formation of singularity, but maybe singularity needs to be hidden by an event horizon and not accessible, not able to communicate with the external observer. So that would be an argument against so-called naked singularities, and would not be referred to as a cosmic censorship. This was never proven in a broad sense. There are many very specific reasons related to this theory, but unlike the first theory, this implication in the other direction is more of a postulate than a proper theory. Right. Nonetheless, now we have a solution in the Einstein field equation to the Einstein field equations. The solution looks weird, but there are good conditions, reasonable conditions that can lead us to this solution. Still, the argument was that, well, okay, so maybe there is a solution, maybe there is a way to get to this solution, but perhaps there is some mechanism in physics that would prevent it from happening in real setup. And the arguments against that, it took another few decades to get there. Like in 1950s, 1970s, 60s, we start to realize that there are objects in the universe that are very bright and very distant. These are quasars. That guy here is Martin Schmidt. He did a brilliant discovery looking at the spectrum of the object 3C273, one of the famous quasars. It looked like a star, but looking at the spectrum, he noticed that the redshift is huge. The redshift, knowing Hubble law, implies the distance to the object. So something that is as bright as star, that would be hundreds of thousands light years away, according to this redshift measurement, needs to be located billion of light years away. So imagine what kind of energy you need to produce. Well, times thousand, times 10,000, millions and millions of stellar luminosities that you need to produce to be able to have an object as bright as a single star, but located thousands and thousands times farther away. And this is these are the quasars. From their fast variability, we inferred that they have to be very compact. So now you have something that is very compact and can produce immense amount of luminosity. There is no star, no object like this that could generate this. So, well, it's like Sherlock Holmes. If all the options that are reasonable to us, given our priors, don't work, then the next thing is probably true. So scientists got back in 1960s to considering black holes as something that maybe happens in the real physical system because of the discoveries of quasars. Well, first of all, black holes don't have any sort of limit on the mass, unlike stars. You cannot have a star that would be massive of a million suns. Second of all, accretion is extremely efficient process. So this is sort of explaining how this very compact object could weigh billions of solar masses and could produce this immense amount of radiation. I'm giving you my biased perspective from a radio astronomer point of view, so I talk about quasars. But another argument was from X-ray community. If you ask them about what was the first identified black hole, they would never say some quasar. They would say it was Cygnus X1. This is a binary system in which we could weight the compact object just with the Kepler law. We know that it's more massive than 10 solar masses. We know that it emits X-ray. To get to this energy, you need to go very deep into the gravitational potential. So it means it's something very well massive, 10 solar masses or more, and very compact. There is no other known object. I will talk about some exotic objects, but the neutron star or any star could not get you there. So this was the argument why Cygnus X1 is a black hole. So X-ray people would say that is the first black hole ever identified. Myself being a radio person, I will say like 3273 as a supermassive black hole, the first one that we identified as a black hole. Again, according to our best understanding and best knowledge. And in the later part of this talk, I will try to undermine our certainty a little bit and play devil's advocate. So now we are another decades later. And in like last 10 to 15 years, we did amazing progress in probing observationally strong gravity. I'm showing two things here. Well, of course, you know what this is. This is the first very strong detection of LIGO, pretty much black holes bouncing and colliding, hearing gravitational waves. We do not only hear black holes interacting pretty much directly, but we also see black holes with instruments of the Event Horizon Telescope, with which we can image the horizon scale emission. And it turns out that if we try to numerically, even analytically predict what would be the image if it was a black hole, it is fairly consistent. So we're really doing kind of semi-direct observations of black holes, both supermassive and stellar ones. So this is the amazing progress of the last 15 years in observational sense, which of course makes us more and more interested in trying to use the kind of observations to tell something more about the theory and about the gravity. Well, what is our best argument for black holes? I think the one that you can really, it's difficult to doubt, is that we really see the compactness of this object. So this is an example from the gravity collaboration. These are the guys who measure the trajectories of stars around the galactic center. They can weight the object very accurately, just with Kepler rules again. And they can estimate the size of the object. For instance, if there is a star going around, you see this orbit, and this object, even if it's dark, cannot be larger than this orbit. This sort of simple arguments. And in this plot, you can see the amount of mass inside a sphere of the size, this size, or this size in terms of mass radius. And you can see that between 10 to the power of 6 million gravitational radii and pretty much of order of 10 or even a bit less, it's the same mass giving you this measurement. So it must be super compact. All of these 4 million solar masses are within of order of 5 Schwarzschild radians. So this we know. We know that from the size of the EHT image as well, and we know that from what gravity identifies as a hotspot, energized features in the accretion flow circling around the central mass, and their orbit is very tight. The orbit is pretty much of the size of the EHT image. These green points are the average orbital points of hotspots circulating around the galactic cells. So we really know that all these masses have to be confined in a very small volume. The solution must be compact. You cannot have broad distribution of some energy field that would be much wider than these constraints.
Can I ask, so for those 10 gravity flares, do you actually see, a reasonable part of an orbit? So that you do.
Yeah.
Both
through astrometry and through polarimetric features, and then with multiple events. So they published that first in 2018 with results where we have simultaneously. The astrometry does the test in 2018, because astrometry really shows you that something is going on. Something is going around, the brightness, the location of the center of brightness is changing. Before, they had light curves, they had polarization. You can argue that, you could reproduce it with a different model on the orbital motion. It is a bit difficult to do it when you simultaneously have astrometry. You know that the brightness is actually going around, and you have polarimetric quantities.
The instruments that you guys. The instruments that you guys.
Not all studies. The study done by Gravity, yes, observed motion, but multiple people, myself included, tried different models. Sub-Keplerian, equatorial, magnetic rich with the component circling on narrower orbit. There is a whole lot of modeling that happened in like last 5 years. I think the consensus is that something is moving, that we know, because of astrometry. The brightness is just circling around. And they have like, I think 8 events in 2023. So it's not something happened by chance just once. Nonetheless, this is something that the interpretation of that is still many people argue.
Right.
I am very convinced that something is moving around.
Yes.
How well we understand what is going on, I will give another talk to the next time. All right, so let's make this little table about the alternatives to black holes. I mentioned 2 features in the black holes that are not exactly defining. The defining feature of black hole is presence of event horizon. But you can turn them on and off. So you have 4 options in total. You have a classic black hole with event horizon and with singularity. You have a regular black hole that tries to solve the problem of this curvature singularity in the center. You can have horizontal singularities, and I'm not saying naked. I will try to I will explain the difference in a while. Horizontal singularities where, well, you have singularity, of course, but it's literally very literal. No horizonless, and singularities, yes. And you have solutions where you don't have either singularity or even horizon. I put them all together, they can be very different. And I know you guys work on bottom stars, among other things. So these are the types of solutions which have neither even horizon nor singularity. Or you may have these very special hairy black holes, some scalar black holes. So that goes somewhere in between. I don't have a proper bucket here for hairy black holes.
Well, they will go generically on the first class.
Technically, they will
be black holes.
They are black holes in a sense of presence of horizon. Yeah. I mean, put vacuum solution.
The generic class.
Yeah.
Just put a human in it.
Right. Okay, so let's now try to go through a longer list of, if we want to have a good alternative to black holes, what are the properties that it should have for us to like be serious about it. Like if it's a good mimicker, what should it have? So this ultra compact is just started. We know, we are like really sure that the solution needs to be very compact. It's not to say that people don't work on on alternatives still. Dark Hebrews, dark matter halos, not that can be more expensive.
I can ask by ultra compact, do you mean that it has a light ring? Because that's typically what
I will talk about light ring, but no, I don't mean that.
okay, because in the literature, ultra compactness is often referred as having a light ring, so that's why I'm asking.
Yeah, I specifically for that I did have here the presence of a photon sphere, but no, I don't require the presence of a light ring. I don't require the presence of a photon shell, as I don't think it is well proven that observational speaking that it exists.
Not even if it's a black hole, so it's
Right. So I don't demand. Okay, so well, I guess you could ask for your solution to be a solution of the Einstein field equations, or if you need to go beyond Einstein field equations, let's make it well motivated. Let's make it some actually involving Riemann scalar. Let's make it hardly to electrodynamics, but something that is well motivated. I will show a bunch of tables like that, and they will be super subjective, and pretty much in every category, you will have a counterexample. So this is sort of like very subjective, my attempt to use the mean value theory. So regular black holes may have problems with this demand that they are a solution to well-motivated field equations. Like, the example is the original solution by Bardeen proposed back in 1970s. That is the first attempt at what we call regular black holes. And it's an extremely simple idea. The idea is that, well, you have a problem because you divide by zero. So you have this curvature singularity popping up. So why not add some delta, that is some constant value that will be tiny and will just avoid hitting zero in the denominator here. Well, it's a great idea and physically not well motivated, but it doesn't correspond to any reasonable field equation. There are examples of regular black holes that do, but the original example is a simple regularizer at the level of a metric, not at the level of the Einstein field equation. And there's a caveat that, well, if this correction is supposed to be tiny, it can be literally blank scale. You just don't want to hit zero. You can hit 10 to minus 18. Why not? This is a finite value. So then it's a very little chance that such a regularization with a very tiny number would have a big impact on the part of the solution above the event horizon that we get to probe observationally. So people do a lot of studies involving regular black holes, this Bardeen solution and other solutions. However, usually they would put this delta value to something of order of unity, meaning something of order of the gravitational radius. That is probably not what you need for regularization. This is a very big deviation that we could possibly test. If it's very small, we don't have access to testing such solutions. Let's.
Can I just? Is it okay if I ask many questions?
I think that's great. Actually.
Yes. Okay. So I mean, this is actually can be made as a solution of linear electrodynamics with a magnetic charge. So you don't.
This is ion gap.
That's right. So you don't put that in the class of kind of well-posed or motivated effective field theories.
This is why it's yellow and not green. As I said, all of this will be very subjective, and I will try to give caveats or give some examples, counter examples to what I'm saying. I'm sort of trying to paint a broad picture. Really, it will be yellow all over the place, and I will try to at least put the red color at least somewhere in the big table that we are going to construct here. Non-pathological in a sense that, for instance, it doesn't violate causality. There can be problems with regular black holes and with horizonless singularities. And let me give an example. This is the solution about which I'm going to talk a little bit in the part of this talk that is now entirely repetitive of kind of like textbook and revision of the state of the art. The simulations that we did with Saura, they pertain to Joshua Lafarina Narayan horizonless spacetimes. Usually in literature it's called JMM1. And the properties of this spacetime is such that it is pathological if you have a special parameter, it's a compactness parameter, and it's smaller than 2.5 mass radii, so just read about the horizon of a short-shift black hole, then you get weird things popping up. The gas that is building this solution would emit acoustic motions faster than light. It's getting weird. But if you go above 2.5 M, actually it is not anymore pathological. It doesn't violate causality. Furthermore, and maybe I will comment on this existence of a light ring. The JMN1 spacetime is a ball of matter. There is a collapse. There is a singularity in the center of it, where it remains some of this cloud of matter. The size of this cloud is RB, and outside of it, it is vacuum. And it does obey Einstein field equations. So it's just Schwarzschild solution about the radius of RB. So when if your radius of special matter, I will talk about the composition of this matter in a bit. If it's larger than 3M, then you don't get Schwarzschild photon sphere in your solution because you have this special non-vacuum GR solution inside. But if you go below 3M, then it's vacuum above your RB, so you will have the normal potential photon sphere of a Schwarzschild solution.
But in any case, it's a naked singularity. Do I understand
No,
correctly?
okay, so let me comment on this now. I thought about commenting about it a little later. So let's try to define nakedness of singularity. So what we will understand, because commonly what functions, what people mention is just the presence of the horizon. Now it is a bit more subtle. We can distinguish horizonless solutions that are not naked. So what I mean when I say naked, I mean if there is a person with a torchlight arbitrarily close to the singularity and is trying to communicate, send signal to the outside world, does the time required for the photon to fly out go to infinity or doesn't? So can you communicate? If you sit arbitrarily close to the singularity, can you communicate with us outside world? If you can, then it's naked. Now, this JMN1 is naked above 3M, and below 3M, it's a null singularity. Meaning that there is no horizon in a sense of a surface, it is like an asymptotic horizon at the point like a singularity. So you cannot communicate in a finite time. If you're arbitrarily close to null singularity of JMN1 type, you try to communicate, your photon will take forever to live, arbitrarily long to live. Nonetheless, there is no horizon in a sense that horizon, there is an asymptotic horizon at the point of singularity. I will show the effective potential, and then it will be a bit more clear from the structure of effective potential.
Do you have Penrose diagrams?
I don't, but it is in literature I know. I will cite the paper which is discussing that, and I will point you to this paper. Right. Well, essentially, it's a null type of
Which are milder. But,
milder in a sense of
that's based by singularities. Yes.
It is, I think, Gresham goes like 1 over.
So there's a divergence of a curvature scale still.
Yes, yes.
But you're saying it's along a null surface.
Yes.
Yeah.
And the Gresham scale is like 1 R to the 4, not R to the 6. Exactly. Yeah, it is a proper singularity, triplet strong singularity, or impedance.
Sorry, Maciek, can I ask a question? Not sure if you can hear me or not.
I do hear you well.
Okay, hi Maciek, it's Pedro Cunha. So a very quick question perhaps. So in this kind of mild naked singularity in a way, is the proper distance from some observer at some finite distance to this naked singularity, is this infinite or finite?
So this is exactly what I tried to describe in this difference between null JMN1 and naked. So it is infinite.
Okay.
Well, the proper time, the coordinate time is infinite. The proper time is null.
Okay.
It
Okay,
is
thanks.
exactly the situation of the event horizon of a black hole, but the event horizon as if it was reduced to the point. And
I see. But the proper distance, so just with a constant time-like section, is that infinite? So, for example, for an extremal curved black hole, the proper distance can be infinite to reach the horizon. The proper distance in terms of just of the spatial section. So, would that happen in this case as well?
So. I think that is the case. But let's take a look at the literature. Okay.
Okay. Thanks.
I think it is.
So I was asking, and by the way, so it depends on the foliation, if it is infinite or not, because of an extremal black hole.
Okay.
But what I said it's milder is because tidal forces still get arbitrarily large, close to the singularity. You don't need to go in a null singularity. Of course, the issue is if the Cauchy problem is well defined. And then, if it is null, then you don't need to set up initial Wilson boundary condition in order to have a well-defined future evolution. But you still have tidal forces which are arbitrarily large, close to the singularity. And those points are points which will affect future evolution of initial data. So it's milder, but it's not completely innocuous. So I would just like to point out that.
No, thanks. It's a very relevant comment. I will talk a little bit about this when I get to simulations that we do. For us, it is a static space-time that we just receive as a background for the simulation. And we don't try to model the evolution in the collapse.
I understand, but you'll have to put a boundary condition for your evolution there.
Yeah,
It's going to be critical, so we have to discuss this.
I'll mention this slide. It is the GR solution. It's a non-vacuum GR solution. Well, it's okay. I will talk a little more about the composition of this one. All right. So that is a very important thing. If you want to be serious about proposing alternatives to black holes, you do need the channel to produce them astrophysically. And well, we have this Oppenheimer-Schneider producing black holes from the gravitational collapse. Now, let me talk about boson stars and wormholes. Well, no, we don't have an astrophysical channel of producing wormholes. I'm pretty sure we don't have a well-established astrophysical channel of production of boson stars.
No, it's not true. That's not true. It's established simulations called gravitational cooling. So we can discuss it, but it's not.
I would be very interested to discuss. So this is another case when you see I put something in red, but perhaps I should do orange, or perhaps I should split.
Well, it should probably split.
And what for wormholes, the only channel that is typically mentioned in the literature is more science fiction literature. Civilization. It feels
well, they have a different topology. So if you start with something with regular topology, you have to go beyond GR.
Yeah, but the point is, it's difficult to imagine like a proper astrophysical channel of production of one. Okay, well, stability. This is a tricky one because I added everywhere. It's a mess. It's a mess. It's a mess. And the color here reflects the amount of literature related to stability of particular solutions. So I would say that this one is pretty inconclusive. For the JMN1 space-time, about which I wish to argue, we have some results about the linear stability. You just pick your solution a little bit, you perturb the stationary state, and it doesn't go crazy. So that's the extent of the studies of stability that we have done for the JMN. Energy conditions, we would like, we may require that well-behaving matter of regular condition is building our non-vacuum solution. For black holes, it's pretty trivial. There is no matter to care about its energy condition. For wormholes, I see again your point that if you're going to make about the boson stars, that in some scalar field that it's perfectly fine in a sense of energy. I will add another column. I will explain.
I don't want to ask, the physical reality of boson stars, but if we want to be accurate, well, boson stars do abide most energy conditions, Of course, you can have models that don't like black holes. You're thinking about electrovacuum black holes, but of course, there's a lot of black holes in many models, which of course will violate quite energy conditions.
I try to capture this diversity with having 4 colors in total, and 2 bits are not enough.
Well, I would say that putting together the boson stars and the wormholes.
Okay. That's a very good comment for my next talk, but you have to suffer through a few more slides when I bundle together boson stars
and of course the issue of stability. Sorry to interrupt you, but the issue of stability and the issue of formation is always very, very tricky, especially because there's big parameter spaces and it can be different in different parts. But you were saying that for the JMN solution, you can formulate perturbations and see they don't grow. But then you have a critical issue, which is what boundary condition that you put at the singularity. So, I mean,
I will tell you what is our boundary conditions.
But your stability there is really tricky.
It is tricky, and I will tell you about the boundary condition that we are doing, but you will laugh at our boundary condition.
Well, no, I won't laugh, but I will be happy to discuss it with you, of course. Yes.
Okay, good. Hi. So maybe that's a good moment to talk or just to mention what kind of solution is this JMN1. JMN1 is a solution of fluid collapse in GR with a fluid with anisotropic pressure. It is a perfectly regular, otherwise altogether perfectly regular, because anisotropic pressure is not anything too weird. If you have magnetic field, you have anisotropic pressure. There is no magnetic field in this solution. It is a fluid that for some reason has an anisotropic pressure tensor, and it collapses from the spherically symmetric condition. And you can show that it collapses to this JMN1 type of solution. So there is nothing else than just not dust but fluid, and this fluid has to have a bit of anisotropy in the pressure. You put it in standard GR, you have all Einstein field equations, you get JMN1 solution.
Can I pick your brain on that? So when you say that you show by an evolution that you form this solution, how do you show this? Because it's singular. Solution is singular. So how do you show from an evolution that it forms a singular?
Yeah, I'm afraid I'm not equipped at the moment to answer.
Is it like it's approaching that solution somehow? Yeah. And you kind of conclude this is the natural final state?
At some point, the compactness, yes, okay. Yeah, in that sense, I can answer this question. About more getting into more complicated because it is asymptotic. It is continuous this collapse, and at some point you have metric everywhere outside from epsilon from the center. That is, it's effectively not changing anymore, and that's we have to cut at some point. Anyway, numerically we cannot go too deep next to the singularity. We have to argue that it's fine to do, which I will try to argue when I get to the simulations part. And when we treat in the simulation the space-time as static. We don't do any attempt at numerical relativity. We do fluid dynamics in the background of this space-time, and we don't go anywhere very close to the singularity. Okay, so that I will have another argument. But we do. How much time do we have? Do we have like 15 minutes? Is that okay, or am I already stretching? I don't know actually.
We have 15 minutes.
Okay, that's good. That's perfect. Okay, because that's like last argument from what should a well-behaving solution be doing. That will be the accretion argument, the theory of accretion argument, not a gravity theory argument. So the two objects that we can look at, the supermassive objects at which we can look at, and the scale of the event horizon in radio with the event horizon telescope are M87 and Sagittarius A star. They are very special kind of solutions. If you have a diagram, it's like a Hertzsprung-Russell kind of diagram, but for accretion. You have optical depth at some fixed radius in your accretion case. It pretty much means denser solution, less dense solution, and how much radiation it produces. So how luminous it is. And you need to solve a bunch of conservation laws for this solution to be a solution to hydrodynamics. And then you have just a couple of regions that admit such an accretion structure. So this is the thin disk of Shakura-Smiayev or Novikov-Thorne, the very famous solution. This is the advectively cooled larger mass accretion rate slim disk solution. And here are solutions that are very low density and very inefficient radiating. Both M87 and Sagittarius fall here without much doubt. For the stability of this solution, for the thermal stability, it's crucial that they can, well, they do have to do something with the energy generated in the flow. So these guys lose the energy through radiation. They just emit a copious amount of radiation and they cool radiating. These guys are very radiatively inefficient. They cannot do it. Something else needs to happen. And ADA stands for advectively dominated accretion flow. In the cases that the energy is just being dragged into the black hole, it just disappears in that way. Before you can release it radiating. So we are cooled because you have very hot ions in your accretion flow, and you just throw away those guys, throw them into the event horizon. Now, if you consider a horizonless object, horizon has this benefit. You throw something in, you don't care. It disappears from your energy balance. It will not stay in the system and bite you later. It will not change into some other form of energy and radiate as the solutions with a surface would necessarily have to do it. So what can happen? Well, if you don't dump your energy in a solution like this into the event horizon, well, it can be carried away in the outflow. Maybe it goes into this compact region and then it's expelled in the outflow, but you have to have really a lot of outflows. You really have to have a lot of this material flying around. Or it can accumulate somewhere in the system, just not go into the innermost region. What I'm arguing is that we are fairly certain astrophysically that you need a sink of energy in both M87 and Sagittarius A star. So if you have this copious outflow, so if you have some accumulation of matter, then it will not be considered. You may get a picture, instantaneous picture of it looking like an image of EHT, but any sort of secular evolution or considerations of spectra would have to show you that you cannot have a solution like that. So I'm saying that you need to be able to dump energy into the central object. Even so, black holes work very well. If you have a boson star, this matter will go somewhere. It will stay, it will accumulate, maybe it will go to outflows, but it will look different than the standard ADA-like solution.
Well, That statement remains to be shown.
Yes. That's right. And I think you guys are very equipped to do it.
In fact, we just put out the paper, actually, we can discuss afterwards, about showing some similarities between also space-time.
Like running simulations that we've been doing for a longer time and like asking, so what is the long-term evolution of this? Okay.
We don't have a singularity.
Well, that is a very positive thing.
And so the boundary condition is actually quite natural.
You can actually model the whole of the domain.
That's right, exactly.
We have to wave our hands a little bit. And this is where we wave our hands. This is our inner boundary in a simulation. There is no physical boundary here. We use 0.1 m as the inner boundary condition.
And we put the equal boundary condition.
We literally put, yes.
Completely absorbing.
Yeah, completely absorbing.
Try any reflection.
We didn't try it yet, we should try it. We see that the solution that we established, we did try the resolution study and like the size of this boundary condition study. And persistently we get that it's like the flow in the disk is supersonic, everything goes in. And there doesn't seem to be anything in a like gravitational structure. These are the curves of the effective potential. And the blue is the solution that we are using in the simulation that I'm discussing. And continuous one are zero angular momentum. The dashed one are with angular momentum. There's nothing special going on. So our argument is that, well, seems like wherever we put this boundary a little farther, a little inner, more inward, the gap is supersonic and it just crosses that. This is not an ultimate proof. It's a numerical observation of the behavior of the system. And what
so in your simulation, you're just kind of damping away whatever matter kind of goes into this region. But physically, it must accumulate there and do something. What does it do?
Sorry.
Physically, it's going in, it accumulates there, it must do something. What does it do? Physically.
It continues to fall.
Yes. So it doesn't kind of bounce back and produces outflows?
Well, maybe at lower area that we didn't test, but the protection will only attract it more. So I would imagine that this.
But then it accumulates, the matter cannot disappear, right? So what does it do?
Oh, so you mean the evolution that the mass of the object will at some point it will.
For instance, it will increase pressure, it will produce outflow. Yeah. I don't know.
Well, so the pressures and all of that, the geometric simulation takes into account.
But then the matter is dumped away, the one that falls into this region, so I kind of ignore it, right?
Yeah. So our only argument that it should work is just with the study of different values of this edge. And it's not impossible because the solution is generally getting hotter. That this gas would well do something. I think what we would worry first before like breaking having feedback on gravity is that we would get totally unphysical temperatures at some point, for instance. And when neutrinos cooling, for instance, that we are not even trying to account, there would be physical effects that could change the picture. We don't do it. So
for the background solution,
yeah.
space-time.
This is
Pressure and pressure.
Yeah.
The diverging. I'm zero or epsilon is a difference.
I don't know that, but it's like a super quick thing to check. I don't know what's the pressure doing. I imagine that it is divergent. So what we assume on the top of the assumptions that I said already, there is nothing in the solution that says that this material building JMN1 solution should not be interacting. We additionally say that, well, we say that it is not interacting with the accretion flow. So, and that way we can really say that, okay, so we only take the metric and we take this metric as a background, and essentially we treat it then as it was an effective vacuum metric, because we don't try to model any interactions. So apart from that, it has to be dark matter. Plenty of that in the universe. Okay, I will try to be very quick, but we have good discussions. So I'm excused for taking a little long time. So let me just, I did mention this JML1, this naked JML1, this is null JML1 that we are interested in. This is an example of a naked JML1. Here also the potential goes to 0, and this is what I mean by this asymptotic event horizon, that the effective potential goes to 0. It doesn't cross the 0. This is the event horizon of the Schwarzschild spacetime, crossing of course to n. This is only approaching 0. So for this JML1, and people did simulations of this object in a paper by Yosuke Mizono with Akhil Unyal last year. However, if you add any amount of angular momentum, you get a centrifugal barrier. So you have this potential barrier that is not coming from this component, GPT times 1, it's coming from this component, and you also cannot accrete. So if you have the naked kind of JML1, you cannot dump matter into it because you have this potential. And it's the same for Eisen-Thomson solution. And actually, it's worse for Eisen-Thomson solution because you have both centrifugal and gravitational potential exploding. These are the simulations done recently by Kluczek and Krajewski. You cannot accrete either. So people try doing this horizontal singularity models, and they have this, what I argue is a problem, that you cannot dump matter into it. This matter either accumulates outside, or you have a lot of outflows because anything that goes in has to go out in the outflow. And this JML1 that we are doing is actually the one that allows matter to go in. Whether it will be so much matter that the pressure will be able to balance, I don't know. I can tell you that not if you go to this boundary, but we are failing far away from the Planck scale. We are at 0, 1, n.
So, but those fields, so if I understand well, that solution is special because even if matter has some angular momentum, it can reach the geometry. But does that happen with any value of the angular momentum?
Well, no, of course. I mean, you can have so much angular momentum that you just swing by far away. You don't even get to the. There is some capture radius that you can calculate, and it will be larger than one of a black hole.
But let's say, so it has to, if something has enough angular momentum to reach the inside the would-be horizon, I would imagine that it may have enough angular momentum to still to not be captured by the central singularity. So
no, and there are no circular orbits inside this RB sphere as well. You can calculate the cross section just through analysis of the geodesic equation. I don't know. I have some plots, not in this presentation, and I'm happy to discuss that. And this particular plot. This particular plot is for the value of angular momentum of I think L equal 3.
So it is like it's small, but it has the same capture cross section as a black hole.
No. Or maybe yes, because yes, I think because it is literal Schwarzschild outside of 2.n. This is inside marginally bound radius, so I think yes, for this one it will be effectively the same as the black hole format. Yes, just because this RB where you stitch Schwarzschild and this anisotropic gas is at 2.8 m, and this is deep inside marginally bound orbit. So yeah, good point. It's same as for Schwarzschild.
But there could be emission from the inner region in this case.
Yeah,
whereas in the
and let's talk about this. So here are a couple of plots about the direct comparison in GRMHD simulation in this background of JML versus Schwarzschild background. You can see all the left sides are Schwarzschild, on the right sides are JML. You can see density. So of course there is matter going all the way, and the boundary is plotted here. It's just that 0.1 m is so small that it's like you have magnetic field with the geometry of magnetic field, so it's forming a very similar MED characteristic to the MED with a strong Boreal component. It's the proxy of luminosity, so it's just how much energy, radiative energy is generated at which pixel, And you can see that it radiates deep inside here all the way, of course, to the singularity or to our inner boundary condition, where is plasma vitality. So this is to argue that outside of this radius, when we stitch the two solutions together, they are fairly similar. And just that when you actually penetrate deeper and you don't meet the boundary of the event horizon. Now, I will really try to wrap up in a second, but let me just show you how it would look like if we were able to observe such a system. So this image is showing you a linear scale of two orbits, of two systems. They are very difficult to distinguish. When you go into the log scale, you can see that there is some brightness deeper inside, emerging from the JML1 solution, of course, because the matter is falling there, it's not stopped by the event horizon, it's not dumped inside the event horizon. So if you look at the cross sections of brightness, this is the brightness, these are the cross sections. The blue solution is the JML1. So the Schwarzschild black hole will terminate. You can actually calculate when it terminates in its equatorial emission. It terminates at 2.81 N about. But in JML1 you can go deeper. And this blue is our boundary condition. You can see there is some pileup around it, and that's the question: is it caused by our boundary condition, or is it caused by actual physics? And the pressure is growing, the temperature is growing, the emission is growing. I think that's the answer, that actually it is highly active. So maybe there would be a bright point if we were able to extend the simulations more inward. But kind of that's the point we want to make. If there is brightness inside this shallow region, it could be an exotic solution. It could be something else than black. Black hole should be dark in this region. These are the results of the playing with equatorial toy model, with redshift, how the redshift structure looks like. So you terminate at 2n for Schwarzschild solution with the orange curves. But with the blue curves, you go here, only your redshift is growing. So the redshift could be over 100 this time. And this is the brightness in the image domain from the equatorial model. So again, you can see that black hole terminates at 2.81 around N from the equatorial emission, but our guy can go on, and it has some emission in the internal band. Let's just take a look at how it looks like, and I think, I'm almost done. So,
is there a question, Rob?
Sorry. I think maybe somebody just did it on mute. So we look at the linear scale here, and they are very similar, and in a log scale you can see all this material going in. So this is a rate-based simulation, rate-based geometry simulation. And you see that they are if you're able to look more carefully. Now the quick question, could we see that? The dynamical range of the HT observations is the order of 10 or 20, meaning the ratio between the brightest feature in the image and the dimmest feature in the image that you can distinguish. And it's very small, it's about 10 or 20. It's not enough actually. But we are just behind the corner, because if we get the dynamic range of order of magnitude, then we could already reconstruct images looking more like this log scale image. So if there is an emission from the region deeper inside, closer to the center of the image, we will know that in a matter of a couple of years, or we will have some constraints on that. That's a better way of phrasing that. We will have some constraints on the amount of emission coming from this inner part. That could maybe point us toward considering some exotic objects. There's another way that you could consider exotic objects through testing of the presence of photon spheres and light rings, but for the sake of time, let's maybe not discuss that. Let's just summarize with this table, which is everything we did before piled together. Very subjective. I will mention this once again. And I added, now I did a separate comment for JMN1, and I added another row here about the problem with the information paradox, which no horizon, no problem. So it's very green. So that's my conclusion. And again, I'm playing a bit of a devil's advocate because we are all very used to looking, of course, but it is very big, I'm just saying. Okay, so this is my very brief summary. I will not read that out loud. Sorry for taking too long, but I think we had really good chat. Thank you very much.
So maybe first I will ask if there are more questions online. Okay, any question here?
Yes.
Yeah, Hector?
So during your talk, it seems that the main strong point for JMN1 singularities is this criterion of having the possibility of afflection, not of getting rid of matter.
This is this is the argument that is kind of not abundant in literature.
But so from that argument, I was expecting to see a plot of the mass accretion rate at different.
Oh, I'm very happy to show you that plot. I even thought, should I add like a backup slide with that one? And then I said, like, okay, I don't have time. I will show you that.
Not necessarily to show, but just to.
Yeah, it's well, as you know, this is a quantity that fluctuates both locally in time, but also where it's like evolution related to the initial setup often. But trying to compare apples to apples, the same setup, the same initial conditions, Schwarzschild JMN, we got about twice lower mass accretion rate for JMN1. Now, for comparison, if we have this like EHT survey of solution, only between MEDs with different setup parameters, you get like more than an order of magnitude m dot variability with black hole magnetically arrested simulations just varying spin or some setup parameter. So there is more variation inside black hole magnetically arrested drift in mass accretion rate that you get to reproduce the energetic flux observed with EHT than between our Schwarzschild and our JMN1. So this is another win for the horizon, which means effectively that we wouldn't distinguish that from because we have sufficient. It's within the ranges calculated with EHT from the survey of magnetically arrested Kerr solutions. But it is twice lower than the Schwarzschild solution.
Thank you.
All right, so well, Maciek will be here for the rest of the week and we'll have lunch now, so feel free to continue to discuss. Let's thank Maciek again.
Thank you very much.